direct variation, part 1. Today we're looking at how to identify direct and inverse variation. First, we're going to start with direct variation. Direct variation has a formula that looks like y equals k times x. This k is called my constant of variation. On a direct variation, as x gets bigger or smaller, if I multiply it by the constant of variation, it gives me my y. The first example we're going to look at is how to determine my constant of variation and how to identify direct variation from a table. So let's say we have an x and y table and we have some values, 1, 2, 3, 4, and 5. And my y values are 4, 8, 12, 16, and 20. The way we can identify from this XY table whether or not it is direct variation or inverse variation is that my y value should increase or decrease by the same amount every time. So if I look at it, if I add 4 to 4, it gives me 8. If I add 4 to 8, it gives me 12. If I add 4 to 12, it gives me 16. And if I add 4 to 16, it gives me 20. Also notice that 1 times 4 is 4, 2 times 4 is 8, 3 times 4 is 12, 4 times 4 is 16, and 5 times 4 is 20. All right, this number that I'm adding each time is my constant of variation, so k equals 4. So when I write the equation for the direct variation of this particular table, it would be y equals 4 times x. So no matter what number I plug in for x, I would multiply it by 4, and that would give me my y value. So this is direct variation with a constant of variation of 4. Now for the next one, we're going to look at another table. So we still want to check and see if it is direct variation. So for this table, we have x and y. I'm going to use the same numbers for x, 1, 2, 3, 4, and 5. But this time it's -2, -4, -6, -8, -10. So we want to check and see if I am adding the same number each time to my y to get the following number. So -2 plus -2 gives me -4. -4 plus -2 is -6. So for each one, once again, I am adding the same number. In this case, I'm adding a negative number. So that means my constant of variation k is -2. All right? My constant of variation of k is -2. So when I write the equation, it's y equals -2x. This would be the equation for the direct variation that gives me this particular table. Now, graphically, we still want to look at the same thing. So if I look at it, y equals kx, this looks kind of like y equals mx plus b, except, in this case, there's no plus b. So if I'm looking at a graph, the main thing is that it's going to be a linear graph. All right, so if my graph has the same slope throughout the entirety of my graph, so this line right here has a slope, or in this case, a k of 1/2. All right, I am multiplying my x values by 1/2. 2 times 1/2 is 1. 4 times 1/2 is 2. So since it has a constant variation of 1/2, meaning I am multiplying my x values by 1/2 each time, it is in fact direct variation. Why is 6 afraid of 7? Because 7's a murderer. Now let's take a look at inverse variation. Inverse variation is similar to direct variation in the sense that it has a constant of variation. The difference is that for inverse variation, it's y equals my constant of variation divided by x. All right, so this is gonna give me a graph that looks very different, but then also if I'm looking at a two-way table, when I determine if it is inverse variation, there's a little bit different way to do that. So let's say I got x and y, so we're looking at a two-way table again. All right, I got 1, 2, 3, and 4. Four and 6. Now, one thing that's important to realize about inverse variation is that since x is in the denominator, as x gets bigger, y is going to get smaller. All right? So as x gets closer to 0, y is going to get bigger. Now, the way we can identify if this is an inverse variation and the way we can find our constant of variation is I'm going to multiply my x's and my y's in my two-way table. If it gives me the same number every time, then that is my constant of variation. So 1 times 24 is 24, 2 times 12 is 24, 3 times 8 is 24, 4 times 6 is 24. So that means my constant of variation is 24. If these weren't the same, it wouldn't be inverse variation. So when I write the equation for inverse variation for this particular scenario, my k is 24 and it's over x. So as x gets really, really small, as in closer to 0, y is going to get larger and larger. As x gets bigger and bigger, y will get smaller and smaller. And when we get to the graph part of this, you'll understand what that looks like. Let's look at another xy table. All right, so I have x, I have y. Once again, we're checking to see if it is an inverse variation. All right, now my values are -2, 0, 2, 4, and 6. -18, 0 is undefined, 18, 9, and 6. So notice that for 0, it's undefined. What that means graphically is that it would be a vertical asymptote. All right, but let's check and see if this gives me a constant of variation. So I multiply my x's and my y's. -2 times 18, -18 is 36. 2 times 18 is 36. 4 times 9 is 36. 6 times 6 is 36. K equals 36. Now, when I write it, y equals 36 over x, here's why 0 is undefined. If x was 0, I can't divide by 0. So I don't have a y value when x is 0, but as x gets really, really close to 0, y gets huge. All right, so let's look at what the graph of a inverse variation looks like. Now, I'm just going to give you the most basic version of inverse variation. If I look at a graph, you should be able to kind of quickly and easily tell whether it's an inverse variation because it'll always look like this. So the only way it changes is that this part may be closer to my origin, this part may be closer to my origin, but notice as x gets bigger, my y values are getting smaller and smaller. As x gets further negative, my y values get smaller and smaller. When I get close to 0, x equals 0, my y values are huge. So as x gets big, y gets very small. All right? So in this case, I could say that this is y equals k over x. This is, in fact, a inverse variation.